starting of an induction machine. Please recall the equivalent circuit we drew. We said if I neglect whatever is my parallel parameter, this was R1, X1. If I include the parallel, of course, this will be XM, this can be RC, which I have not included almost until now, but nevertheless, if I want to include the iron losses, this should be included. Then I am going to have X2 dash, I am going to have R2 dash by S, which has two components clearly. One is inherent loss that takes place, which is R2 dash, and the other portion is the mechanical output, which is R2 dash by S into 1 minus S, right? And then this is going to be short circuited. This is the normal equivalent circuit of the induction machine, with V1 being the input voltage, or Vs, whatever you may call it, stator per phase voltage. When I am going to start the machine, speed is 0, so the slip will be 1, right? So at starting, slip is 1. Because slip is 1, I am going to have the starting current, if I try to write, neglecting even the magnetizing current, I should be able to say it will be V1 divided by R1 plus R2 dash the whole square plus X1 plus X2 dash the whole square root of this. This is what is going to be my starting current, right? So I eliminate S completely here because S is 1. When S was not 1, I had this S to be 0.01, 0.02, 0.03, whatever. So if I assume R2 dash is 1 ohm, for example, it will be multiplied by the factor of 33 or 50 or 100, as the case may be, depending upon whatever the slip is. So this entire rotor impedance is going to look bloated up, right? Because of which automatically the current will get decreased. The rotor current will get decreased once the slip becomes really a small value. But when the slip is 1, this impedance, whatever impedance I am looking at, is very small. Because this is very small, I start is high. This is going to be really high, right? So it is definitely not a good option to start the machine directly by applying the three-phase voltages, which we call as DOL. We call that as direct online starting. So direct online starting of an induction motor is definitely not a good option. It's a self-starting machine, agreed, but it is not going to really help us if we are trying to start, let us say, a 100 kilowatt induction motor directly by applying the three-phase supply, because the current that I am going to draw will be as high as 5 to 8 times the I full load. If I say I full load is 10 ampere, I might draw as high as 70 to 80 amperes when I am connecting it directly to a three-phase supply. So normally power system authorities put a limit on what is the rating of the induction motor you can directly start. Generally beyond 10 kilowatt, we are not allowed to start, at the most 50 kilowatt. If you go beyond 50 kilowatt and then you try to do direct online starting, in all probability your power supply will be revoked. Power system authorities will take a pretty stern action because it affects all the other people. Please understand, I am going to have a transmission line, maybe here is my source, and I am going to have a long transmission line like this. The transmission line has certain value of resistance and inductance, definitely, right? So if my factory is located somewhere here and I am going to draw a huge current, right? This is a large current. Then I am going to have lot of drop taking place all over in all this R and L. Everywhere there will be drop taking place. So a next door neighbor who has another factory, probably, if they are looking at the voltage at this point, I am going to have really much lower voltage when I am starting the machine. So, normally it may be 400 volts, now it may be 380 volts or 360 volts. So, it is definitely not good for the equipment that are connected in the same line closer to my industry premises. So, generally there is kind of an understanding existing between the electricity supply provider and the consumer, saying that you can't use these loads. Welding, for example. If you try to weld directly from the power supply, what will happen is, because it's a short circuit, most of the times welding happens when there is an arc struck and then you are going to put the electrode right there. So it is a short circuit. So you will see that the current drawn is very high, the voltage will dip. So it is really, really dangerous for the other equipment which require constant voltage. So you can't connect those equipment in the same line, or you should put a restriction on the equipment that can be used or it cannot be used. You have to say this is the limit. That's it. So DOL starting normally is used only for motors less than strictly 50 kilowatt rating. In fact, even for 10 kilowatt rating, maybe until 10 kilowatt rating, it is okay to use it. But definitely not for greater than 50 kilowatt rating, right? So I should have some other method of starting the machine. So another method of starting which is very commonly used is star delta starting. So in star delta starting, normally we assume that the motor stator winding is connected in delta. So this is the motor winding. Okay? So if I am connecting the motor winding in delta and let us say I am applying certain voltage, I am going to have in this case V line equal to V phase. Right? And let us say the impedance of each of these phases is Z. Right? So I am going to have whatever is the current that is being drawn in terms of RMS value. If I try to do, I should say V line divided by Z equal to I phase, which is also incidentally V phase Z divided by Z. Right? Whereas, if I try to look at line currents, right, what is drawn from the supply, what is the motor drawing is different, what is actually drawn from the power supply is √3 times that motor current, phase current. And so power system authorities are going to look at only this √3 times the phase current, right? So, I am going to have this I line to be √3 times V phase divided by Z, right? Rather than this, if I try to make initially the winding get connected in star, I don't want it in delta, I want the same thing in star, right? So I will still have the impedance to be Z, Z and Z. Nothing has changed. The same winding I am reconnecting in star, right? And I am going to have essentially the voltage, the same voltage is going to be applied. So here we call this as V line. So I am going to again call this as V line. I am not changing anything. The same power supply I am connecting to the motor, but I am going to connect the motor windings in star format. That's all. So in this particular case, I can say V line is equal to √3 times V phase, right? So what I am applying across each of the phases is only V phase, which is V line by √3. So I can say I phase is going to be V line divided by √3Z. That is V phase divided by Z. And incidentally, in star, this is also I line, right? So if I try to look at the ratio of I line delta and this is I line star, I can say I line delta is equal to 3 times I line star. Right? So I'm going to have 3 times. So by doing this, I'm essentially reducing the starting current, no doubt. But what happens to the starting torque? That also we'll have to check. We said that the torque is proportional to current square, right? You remember we wrote it like this, I2 square R2 dash by S omega S times 3. This is what we wrote as electromagnetic torque. Right? So I can say simply whatever is the current that is being drawn, square of that will be corresponding to torque. So I can say TE in delta condition is proportional to, I should say, V phase square divided by Z square. Or I can say V line square divided by Z square. That is also fine because V phase and V line are the same as far as delta is concerned. Whereas, if I try to look at what is TE in star condition, that will be proportional to V line square divided by 3 Z square. So, I am going to have again TE delta will be equal to 3 times TE star. Right? So the torque is also going to get decreased by a factor of 1/3. When I look at the delta torque will be much higher. So we are taking a hit on the torque generated by the machine, no doubt, but we are also reducing the current. So it's not a great option if I am trying to start an induction motor which is probably coupled to a hoist, coupled to an electric vehicle, or coupled to an elevator, because those things require a high starting torque. Whereas here the torque is going to be very, very limited. I'm not going to get a good amount of torque. So if I had started it in delta, maybe my machine would have started, my system would have started. But if I'm trying to look at it after connecting in delta, a star, I'm not going to get a good amount of torque. So these are applicable mainly in those applications where I do not require a large starting torque. Typically fans, pumps. If you look at fans, torque is proportional to omega square. Load torque is proportional to omega square. So if I look at fan or pump drive, I can say TL is proportional to omega R square. So if omega R is really, really small initially, it doesn't have to displace a large amount of air surrounding it. So obviously, when I start, I will require very small torque. As I go up the speed, I will require more and more torque. So this is very much applicable to fan or pump drive, and this star delta starting is very commonly used in agricultural pump sets. So star delta starters are very commonly used in agricultural pump sets because most of them require very, very small torque during the time of starting. Not a big deal. And generally there will be a time delay. It will be in star for probably 0.5 seconds, 0.7 seconds, and after that automatically it will switch over to delta. So when that happens, both ends of the winding should be brought out. I hope you understand. If I am going to have A, B, C, 3-phase windings, I'm going to have this as A, this as B, and this as C. So if I want star, I have to actually have contactors here and contactors here. These two have to be, so these are starting contactors. They will be closed. and I'm going to have A, B, C, three-phase supply applied here. Right? So this will be the starting contactor which will be closed. And if I want really this to be connected in delta, I will have something like this. From here, I will have one contactor. So this will be during running. Right? One more I should have like this. So this will be again running contactor. And the third one has to be connected basically between this and this. Right? This will be the another running contactor. So starting contactors will be opened out, running contactors will be closed, and then it will become connected automatically in delta, and then it will pick up a higher torque after that. Right? So star delta starting is very, very commonly used in agricultural pump sets. But please note, when I am opening the starting contactor and later on connecting it in running contactor format, there is a break in the circuit for a very short while. So your load should be able to withstand that. Because it is pump, it's all right. It's just delivering water. For a short while, if little bit of reduction happens, heavens won't fall. So these are okay where very great accuracy is not really demanded. Right? So this will have a break in the circuit definitely when it is changing over from star to delta. And one more problem also can be, I have some back EMF always, right? Like a transformer, I will definitely have a back EMF. Flux may not collapse right away, so I will have some amount of back EMF definitely. When I break the circuit and reconnect the circuit, whether the voltages that were induced and whatever is the voltage that is coming from the supply line, if they are in complete opposition, I will have a huge amount of current. They can be 180 degree out of phase, very much. Why not? Right? You get my point. If I'm going to have the back EMF somewhat like this, whereas I'm going to have the applied voltage somewhat like this. That is being applied between this point and whatever is the induced EMF. So each of these windings have to limit a very, very large current if the two back EMFs, that is the back EMF and the applied voltage, are completely opposing each other. Right? They are 180 degrees out of phase. If they are actually in phase roughly, then I will not have so much of voltage being withstood by the motor winding. So these are generally inherent problems that are faced in such applications where I'm going to break the circuit and reconnect the circuit. So this is breaking the circuit and reconnecting the circuit once again. So this is one of the problems normally we may face in star delta starting. So one is EB, the other one will be V applied. So if they are completely out of phase, then I'm going to have a major issue. Right? So there are more methods of starting which will also give me somewhat accurate starting that is possible within certain duration of time and so on. So we looked at DOL, we looked at star delta starting. The third method of starting that we are going to discuss is auto transformer starting, which you used in laboratory. In electromechanics lab, generally what we were using is with an auto transformer. We always had a three-phase auto transformer. So what we are actually looking at is, here is the three-phase supply that I have, and I am going to have a three-phase variac. I am showing it as though it is star connected. So this is how it is connected. Right? So this is A, B, C, and this is the three-phase variac. Now I I'm going to have my induction motor here. Just to differentiate between these two, let me probably draw the induction motor winding. Again, I am showing it in star. It need not be in star. It can be in delta as well. So this is how it is going to be. So this is actually the stator and here is the rotor. I am showing squirrel cage rotor. So this is the rotor, this is the stator. So overall this is the induction motor. Okay. Now from here I am connecting this probably to one of the faces. I am again connecting this to another face. And I am connecting it to the third face. Right? Please note, I am applying a very small portion of the voltage because this is the jockey point or the variable point. So, I am applying, if there are 100 turns, I am probably applying only corresponding to 10 turns. Nothing more than that. So, I am applying very, very small amount of voltage in a balanced manner. All three phases are balanced because the three-phase variac jockey is moving, in a balanced manner. So, I am going to have actually, if I try to look at just one single phase winding, here is my variac, this is the power supply, right? So, this is V supply. And what I am doing is to connect a jockey point and then I am going to have this applied to the motor. Right? So if I say that there are n number of turns here, whereas I am just applying only one turn, for example, n:1 is the ratio of the voltage of the supply to the voltage applied to the induction motor. So I am going to have actually the current through the motor, I phase of the motor is going to be V supply divided by N Z. If I say this is Z, impedance is Z. Right? This is how it is going to be. So obviously, if I try to look at the torque, because the torque is proportional to I square, I am going to have torque with variac is going to be proportional to V supply square divided by N square Z square. If I had not had the variac, I would have got the torque to be V supply square divided by Z square. So the torque has decremented or decreased by a factor of 1 by N square. Right? So I am going to have reduction in the torque is by a factor of 1 by N square of TE original. If I try to look at what is the original torque, compared to that it is going to become 1 by N square. Right? But if I actually look at the current here, because I am going to have n:1 as the voltage ratio, the current would become 1:n, right? Because I am going to have V1N1 equal to, V1I1 equal to V2I2. So I can say in this case, if I just say this is V primary or V supply and this is V motor. So I should say I supply divided by I motor will be equal to V motor divided by V supply. Right? This is valid always. So I am going to have essentially I supply equal to whatever is I motor divided by N. Right? And I motor is after all V supply divided by NZ. So I am going to have this to be V supply divided by N square Z. Right? So the current current as well as the torque, both are actually decremented or reduced by a factor of 1 by n square when I am using n:1 as the turns ratio of the primary side to the secondary side in a variac. So it is very, very similar to star delta starting. If I assume that instead of n:1 I have √3:1, you would not see any difference between the star delta starting and this auto transformer starting. If I assume that I still have the motor winding connected in delta itself, but I'm going to have √3:1 as a variac which is inserted, it will behave exactly similar to a star delta starter, right? So this method is also really not good. This method is also not good for loads requiring high starting torque. If I require a very high starting torque, this method is really not going to work very well. Right? So this essentially tells us about the third method of starting, which is auto transformer starting. There is one more method of starting. The next method of starting that we would like to look at is impedance starting, which is very similar to what we did in the case of DC motor. In DC motor, we inserted a large armature resistance. Similar to that, I will insert a large impedance in series with my power supply. Let us say here is the three-phase supply I am getting. So I'm going to insert one external impedance like this. So these are the three-phase impedances. So I would say R plus jx, this is also some R plus jx, and this is also some R plus jx. And then this is connected to my three-phase induction motors stator. So this is my three-phase induction motor. So I have just connected it like this. So these are the three-phase supplies, A, B, C. So the overall current drawn will get decreased because originally we wrote the expression to be R1 plus R2 dash plus now this R will also come into picture. This will be the total impedance. Similarly, I will have x1 plus x2 dash plus x the whole square root of this. This will be the total impedance, and this should be in the denominator, and V1 is the voltage that is being applied. So this will be I phase. So the per phase current will get decreased because of the inclusion of R and X from external to the motor. So I will have the reduction in the current, but definitely I will have reduction in the torque as well. So the same thing what I just told you holds good. Right? If you actually look at the induction motor, during starting, right, you are essentially looking at, during starting you will essentially look at the equivalent circuit like this I told you. This will be R1 plus R2 dash, and I am going to have X1 plus X2 dash, and I am going to apply V1. This is what is my starting condition of the induction motor. I do have definitely a magnetizing reactance because I have to establish the flux. So the magnetizing reactance, as an approximation, I can show it here. It is an approximation clearly. So this is my XM. So if I look at the power factor of the motor, it will not be very good during starting condition also, because you have R1 plus R2 dash. R2 dash is generally small, squirrel cage induction motor, thick rotor bars, So I will not have much resistance. R1 might have some amount of value, and X1 and X2 dash, if I am looking at, I am really not going to have very small value because there is air gap. Leakage is going to be somewhat pronounced. So X1 and X2 dash actually are going to be the leakage values which are somewhat larger. Xm actually is also going to draw a good amount of current because I have air gap. I can't help it. So we will see normally that the starting power factor is not good. Starting power factor of an induction motor is not good. So if it is not good, in that case, right, if I include R and JX, they will also meddle with whatever is the power factor that I am going to get. If I include more X rather than R, then I will have very bad power factor, but I will not have much of heat losses. If I include more resistance but less X, then the power factor may be fairly good, but I will have a good amount of heat losses. So I have to decide what really I want. If I have a good cooling arrangement, but I'm going to take care of the power factor much better, then I might try to include a larger resistance and smaller reactance. But nevertheless, this is a lossy method. It is not going to really give you a good performance in terms of good amount of starting torque. The starting torque is going to be still limited. That is one of the problems that we are going to face with respect to this particular method of starting. Right? So the impedance starting can include large R, less X, less R, large X, or all of them almost equal to each other, depending upon what is the kind of requirement you have. Can we have an AC voltage controller to start the induction motor? We had looked at AC voltage controller earlier in power electronics course. This is also generally termed as soft start. So you are essentially trying to look at changing the voltage that is being applied to the induction motor. So I can just have the RMS value. So RMS value of the voltage applied to the induction motor is increased slowly. So this is done with the help of, let us say, one thyristor in this direction, another thyristor in this direction. Similarly, I am going to have 3 pairs, right? This is second pair, and I am going to have the third pair like this, right? These are the 3-phase power supplies, A, B, C, and I am going to connect this to the induction motor. So let us say this is connected like this. So I can start with the firing angle of 100 degrees or 120 degrees. I can start off with a large firing angle. So I am going to look at it as though if I just look at one particular phase, if this is my applied voltage, if I look at a firing angle of 100 degrees or something, I am going to apply only this much of voltage and this much of voltage. Nothing more than that. Right? And slowly I can vary the firing angle such that it decreases as the machine picks up speed. As the machine picks up speed, I will have more back EMF generated, so that will automatically bring down the current. At that point, I can try to reduce the firing angle. So alpha is decreased as speed picks up. Right? So this will essentially vary the RMS value of voltage that is being applied to the motor, and I can have a complete control because I am looking at the firing angle being changed at my own will. So I should be able to definitely adjust the amount of voltage that is being applied as per the requirement of the motor and load system, right? So this sounds like a good option, provided again the starting torque requirement is not so high. The starting torque requirement, if it is high, again I am applying only lower value of voltage. Then how will I get really a good amount of current or good amount of torque? So this is also definitely not good for if high torque is required. If high starting torque is needed, this is not a good option. This is definitely not a good option. And one more major problem is harmonics. We are definitely not looking at sinusoidal voltage or sinusoidal current. Everything is non-sinusoidal. So the motor can have third harmonic, fifth harmonic, seventh harmonic, and so on and so forth, and which can really interfere with the proper working of the motor. We will look at how the induction motor behaves when I am actually feeding it with harmonic rich supplies. As we are going to inverter fed induction motor, at that point we will talk about that in greater detail, right? But it is definitely not a good option to feed the induction motor with unnecessary harmonics. That is not a good option at all. So this actually, whatever we discussed so far, all of them are applicable to both squirrel cage as well as wound rotor induction motor, because I am interfering with the working of the induction motor from the stator side. Whatever we did so far is from the stator side. So that definitely can work for both wound rotor induction motor as well as the slip ring induction motor, as well as the squirrel cage induction motor. So if we are looking at another method which is only applicable to the wound rotor induction motor, this is rotor resistance starting of wound rotor induction motor. Right? So we are actually looking at, if you actually draw the wound rotor induction motor, I should show somewhat like this. This is my stator. Stator is essentially the same. So as far as the rotor is concerned, in wound rotor, normally we show it with 3 windings like this. They are connected to the slip ring. The difference between squirrel cage normally we show it like this. I have the stator here. This is the rotor. Rotor we show it like this. This is essentially showing the rotor bars. So this is the representation of cage induction motor, whereas this is the slip ring induction motor representation. Okay? You guys know DC motor. DC motor is always represented like this with the 2 brushes, because I see still some kids drawing the induction motor and then showing 2 brushes. Please do not ever do that. If it is a 3-phase induction motor, you can't have brushes, protruding from 2 ends. Definitely not. Representations are extremely important when you draw a diagram, right? So now these are the 3 terminals of the rotor that are brought out. I can have additional resistances connected here, but of course they will be 3-phase resistance. So if I have multiple number of resistances connected like this, I can short circuit them as the speed increases further and further. So I will have normally contactors connected across each of these resistances like this, which can be closed as the machine gains speed further and further. So I'm just showing contactors for each of these resistances. Right? So similarly, I will have contactors for the next resistances as well. They'll be closed as the motor gains velocity further and further. Right? So if I say that this is R external together, think about the expression we wrote for induction motor. We wrote 3I2 square R2 divided by S omega S. This is what is TE. Right? If we are neglecting the magnetizing current, I should say I2 dash is equal to I1 if IM is neglected. If I neglect the magnetizing current, I should be able to write like this. Right? So I can simply say, if I am looking at TE starting, I should be able to write this as whatever is my starting current whole square multiplied by R2 dash divided by omega S, because S is equal to 1. Right? I'm going to have the slip equal to 1 during starting. So I can directly write T starting like this. So if I try to look at this expression, I am having R2 dash coming into picture. So if I am able to increase the rotor resistance, not only do I reduce the starting current, but I also give an increment to the starting torque. So if I can somehow tamper with the rotor resistance, that will give me two advantages during starting. I'll bring down the starting current all right, but the reduction in the starting torque, what I got in squirrel cage, there I had to tamper it only from the stator side. I can't even tamper anything in the rotor side. I can't touch the rotor side. Whereas here, I will be able to touch definitely the rotor resistance. I will be able to modify the rotor resistance. So I would be able to get a good amount of starting torque as compared to squirrel cage. That's all I'm trying to say. Right? The same thing, if I'm not able to bring down the current, I would have gotten better torque, no doubt. But my sole purpose is to bring down the starting current as well. So when I am bringing down the starting current, am I reducing the starting torque also drastically? If I look at it that way, I would not be really reducing it drastically as compared to squirrel cage induction motor. Right? So rotor resistance control actually will be advantageous in several ways. One is definitely the current comes down, no doubt. And torque does not get as reduced as in the case of cage motor, because I am going to have this resistance parameter even coming up in the numerator. Right? I am going to have R2 dash plus R external, whatever is the external resistance that I am including. Right? And obviously, power factor will also not come down. Power factor will be fairly good. I would not say very good, but fairly good, because I am going to have, please recall the equivalent circuit. I will have R1, X1, Xm. Then I am going to have R2 dash plus R external dash, both divided by S. And I am going to have X2 dash. This becomes my equivalent circuit during the time of rotor resistance starting. Right? Okay? basically we looked at all these methods of starting common to both the motors except for the last method where I'm going to tamper with the rotor resistance alone.